It is my great pleasure to introduce today's speaker, Dr. Andrea Thorn. But before starting, I would like to briefly introduce her. She's a very multifaceted person. She's a crystallographer, a structural biologist, but also a really great method developer. She first studied molecular science at the University of Erlangen, after which she moved to University of Göttingen to do her PhD with Joel Sherdwick. I think she was one of the last of his PhD students. And amongst other things, she was also working on the ShellX program, which some of you might use. After her PhD, Dr. Thorne did several postdocs and was, amongst others, a recipient of a Marie Curie Fellowship, for which she stayed at Cambridge. Later, she was a senior research scientist for a short while at Diamond Light Source, and amongst her postdoc time, she started also working on cryo-EM. Dr. Thorne won several awards, for example, the Rising Star Award by the Asian Crystallographic Association, and she is really highly engaged in the crystallographic community. So she's a member of the IUCR Computing Commission since 2017. She's the vice president of 9, the computing section, as well as the chair of the Coronavirus Structural Task Force, for which she also received a very big research grant last year, almost 2 million, which is really impressive, but also shows the high importance of the project. She does a tremendous work of outreach, like since very early on, but especially these days, where she really tries to communicate to the public why is research important, what is corona, how does the virus work, etc., which is really great and important. She's currently a group leader at the University of Hamburg, where she has a very dynamic and active research group of 13 people. And to my understanding, she's also currently looking for a professorship in Germany. So if you know something, please drop her an email. Without further ado, it is my great pleasure to welcome Dr. Thorne, who will be talking today about understanding COVID-19 through molecular structures. Please.
Thank you very much. Just one small correction. We received the 2 million for methods development work and just were allowed to deviate some of the money into coronavirus work later. So it has to be noted for future generations that it's well possible to get big grants for methods development projects. This is an ongoing rumor in the society. You can't get money for methods development. I would contradict. But thank you again for having me. It is a great honor to be the first speaker in this series. And I do hope you can see my slides. Does that work? Yes. So I'm going to talk about this task force, but also about some other things my lab does. And yeah, here we go. This is the virus, or as we see it. Just for the people who come perhaps from small molecule crystallography or other fields within the European Crystallographic Association, I quickly would like to remind everyone that even though the virus is fairly big, it consists of atoms, just like everything else. And these are big so-called macromolecules, biological macromolecules. Here you can see the spike of the virus. And if we zoom in, we see inside the surface representation, the so-called ribbon diagram, which have been developed by Jane Richardson a few decades back. But we can also display this molecule as individual atoms. And that is then way too confusing to analyze anything. And this is the reason why most pictures I'm going to show you here are going to be ribbon diagrams and surface representations, but they actually stand for individual atomic positions. And in the first part of this talk, I'm going to talk about what we usually do when there is no pandemic and we're not looking at coronavirus structures. And then I'm going to tell you how this work basically led us to do coronavirus things. And then in a short section at the very end, I am going to talk about life during the pandemic and within this rather unconventional research project that we started. So where do structures in macromolecular crystallography or NMR or cryo-EM actually come from? Well, first you do a biological preparation. I'm sorry, this is only one box. It is usually a majority of the work to find good conditions for purification and crystallization. And then we do a data measurement, doesn't matter which method. But then for the interpretation of these measured experimental data, which constitute the result of the experiment, for the interpretation, we need a model, typically a molecular model consisting of individual atoms. And only if we have that model can we answer the big biological questions that may follow, such as, for example, how does the coronavirus bind to the host cell? Also dependent on the model and often forgotten is a lot of downstream methods. Over 90% of downloads from the PDB are not made by people who have ever deposited to the PDB, meaning that most users of protein data bank data are actually not experimental structural biologists. They are bioinformaticians, drug developers, and they are using these molecular data as often as a kind of ground truth, for example, in the AlphaFold project. So everything depends on getting the model right. Problems, however, are that sometimes you can find in the PDB ligands, which look like this. This is an example from Bernhard Rupp. And I'm hoping that you will all know your chemistry well enough to know that molecules don't usually make such sharp angles, and also this should be one molecule and there's clearly something missing here. And yeah, it's mangled. This is one problem that can happen. So the interpretation is wrong according to prior knowledge. We know chemistry must look different. It can also happen that we can't solve a structure although we measure the data set. But the most insidious of all is we get an answer and we think it is correct and we publish it in Science. And then it is wrong. And that this happens is not the fault of structural biologists. It is because of the complexity of the problem, I would argue. And this is what we concern ourselves with. However, we don't want to be the people who just point out the problems and say, bad crystallographer. That's clearly not our goal. We want to make this better. And first in this stands the question, does the structure fit the data? And this is measured in crystallography by an R value. You're possibly all familiar with it. It gives you the discrepancy between the data you measured and the model you have employed. It should be small for a good structure. And this is a typical part of an experimental map, 60S proteasome. And the R value here is 20.4%, which is also fairly typical. What we would like was 0%, where model and data fit together really well. That would be ideal. I mean, we possibly can't have that because of measurement errors and other things, but that's what we would like. Now, small molecule crystallographers typically have about 5%. They can, even with a home source, get structures of organic molecules that are like 2.5% R value. We, as macromolecular crystallographers, can only dream of such values. Our structures are typically in the range of 20%. And if you think about this number closely, and without thinking about an individual structure, it is pretty obvious that at a mismatch between data and model of 20%, meaning only 80% of your model actually reflect the data, there may be a few things missing. But what are these things? Does this mean the data aren't really good? Is the data quality the problem? Did we miss something very fundamental about what protein models should be looking like? Is the optimization, maximum likelihood or otherwise, of the model onto the data not ideal? This is one of the big questions that I would like to address in my research career. And one problem which exacerbates this whole issue in crystallography is the fact that we cannot measure the phases directly. So from your X-ray data, you get the amplitudes, and then you would like an electron density map like this one, but in order to interpret this, you need a map, but you can only calculate it with phases. And the phases typically come from a model, be it in molecular replacement, where you placed a model, but even in experimental phasing, you're employing density modification and hence making some rather strong assumptions about the nature of your crystal before you even get a map. So we can often not see what we don't expect. And this can be seen in the model interpretation for this map. You can see that the map really doesn't fit so well to the molecule. So the phases may be at fault, and phase error is typically large in macromolecular crystallography. And this, I think, accounts at least for part of the problem. What else could be missing? Protein crystals, crystals of macromolecular organic molecules, have large areas of disordered solvent. This has been known in 56. It's like, I mean, even before they had the first protein structure, they knew this. 46, half of the volume of the crystal is typically disordered solvent. And it's not only water, it's like ions and PEGs and glycerol. And it makes our crystals squishy too. So it heightens mosaicity. And we are modeling this with only 2 parameters. One consequence of this large solvent area is also that each individual macromolecule in the crystal is ordered slightly differently as it is exposed to different solvent conditions. And the consequence is that we are observing an ensemble of similar folds, which is called the ensemble problem, instead of one structure. This may be exacerbated by problems of dynamics and lattice vibrations, although we are really unclear on those. And it just conclude again, we cannot observe what we do not expect in crystallography. And this is a big problem. And one way to look at this, which I kind of like failed at, which is why this is not published, is you can look at the difference between FOPS and FCalc against resolution. If you calculate this in resolution bins for, in this case, 200 random structures from proteins, you can see a kind of systematic behavior, meaning that the mismatch between model and data follows a certain regularity in terms of resolution. And with that, in terms of the size of the feature that is causing the difference. But what is that feature? So when I answered that question, I'm going to publish this. But I kind of like hammered my head against this problem for 2 years and couldn't get anywhere, which is why I kind of came back to what I have shown in the beginning. Oh, by the way, there is this like 3 tiny spikes. I don't know if you can see them. I'll come back to them in a minute. So remember that. Why not cut out the model? We need to get the phases elsewhere. And we need not to use any kind of like prior knowledge. So I tried to do this the simple way and I kind of failed. And then we now got a little bit smarter and we now have 2 data sets where I think we may be able to get our phases without employing a model with help of Armin Wagner, Diamond Light Source. And I have a new PhD student, Max Edich, working on this since a month. So I'm pretty excited. He's currently learning how to use Sharp and how to do refinement. And he's reading a lot of books because he's still in home office. So I'll come back when I have something to the next ECM conference in Versailles, perhaps. Another problem are the data. So we look at data, for example, as average intensity versus resolution. Average intensity versus resolution. This is called a Wilson plot. It typically looks like this. But if you do an individual point for each reflection, the picture kind of changes. And what you can get looks like this. And as you see, this has 2 spikes, by the way. These are the same effects that we've seen in the plots of FOPS minus FCalc. And these things are ice rings. And these ice rings have not been background corrected in the integration. So they made it all the way through integration, scaling, and merging, and ended up in the protein data bank in the integrated scaled and merged data set as a bias to all reflections at this resolution and that resolution. So that's not pretty good. And we found out that this may affect 20 or more % of all entries in the protein data bank. So the error is not huge. It accounts at a maximum to 5% R value. But it is relevant. And the problem was also that we could recognize this from these plots, but we could not recognize this automatically very well. So we published something called the IceFinder score, which was better than Phoenix X triage and C-truncate. And then now, like 2 months ago, Moreau et al. Published their score, which is much better and has 94% accuracy. And now we have trained, before their paper come out, actually even a machine learning algorithm to find these spikes in the pictures. And that finds ice rings with 98% accuracy. And I hope to submit the paper to ACTA next week. We also found many other problems making these plots of intensity versus resolution, which really shows that sometimes you just have to pick a well-hidden low-hanging fruit. I guess other people have done intensity versus resolution plots before, but perhaps they didn't ask long enough why they were looking weird. And we could remove quite a lot of bugs, and we also found some really weird things with X-Files. And so now we're having a big collaboration, and that's actually the larger of the two grants, in which we are analyzing how common certain diffraction data problems are, what the implications for processing and structure solutions might be, and how we can have better automatic identification. And we do all of this under the frame of a program called Auspex, which also has a web server, but is also available from CCP4. And you can find it under auspex.de. And there, under examples, we also comment on each and every kind of like problem that we found that we could explain. We still have a bunch of them that we couldn't explain. So this is what we normally do. And I suspect that I wouldn't be invited for a lunch seminar for these things, because we work out of the spotlight. We usually help people with their problem structures, develop new software, teach people how to use them a lot. But methods developers are just not the people who win Nobel Prizes. We are enablers of scientific projects and are usually in the shadow somewhere backstage. Oh, this I quickly wanted to show you because I think it's exciting. We last year developed a reciprocal lattice viewer with the chair of games engineering in Würzburg in the Oculus Rift. So this is not quite as cool as it is when you're actually wearing the thing, but it can help you indexing, and we hope to continue developing it a little bit. If you're interested, please let me know. And yeah, you can use it to identify twins for small molecule crystals and macromolecular crystals, and kind of like do this with a panoramic view of reciprocal space. So we thought that was fun and a very good case study on like scientific application, which is why the chair was interested in doing it. So coming back to more serious business, errors in structure are normal. They're a matter of fact. They happen all the time. We as a community need to accept this. Errors happen. They're not a personal fault of anyone. You can do a lot to try to avoid them, but chances are that if there's a PDB entry, I'd be still able to point to some problem there. I mean, this is just how it is. And we should avoid the really bad ones, which lead to retractions. And we should try to get as much as we can out of our data. But the fit between data and model is not perfect. Complete automation is not yet possible because the problem is really so borderline. Models are therefore mostly built manually still. Expertise in different aspects is needed. So you need to know whether it's cryo-EM or crystallography. You need to know how you made your data, how you process your data, how the experiment is set up. Usually you know the biological preparation beforehand. You need to know about the chemistry that may occur. You need to understand the nature of your specimen really well, and you need to know all the software that is used in the entire process, from the like beamline control software down to the validation and the position. And I would guess that this is just too much. So for the average structural biologist, who usually spends like 70% of their time in the lab trying to purify a protein and crystallizing it, we can just not expect all of that expertise in one place, and should treat the model, in my opinion, as a proposal for interpretation and not as the absolute truth. That would resolve a lot of problems. We could also think about whether models should be versioned, because models that were built 20 years ago can be improved with modern software. So, however, we are kind of specialists in structure solving and problem structures and knowing when the software hasn't made a mistake. Now I'm going to quickly talk about SARS-CoV-2. So this is a life cycle we made in collaboration with the animation lab at the University of Utah. This is what is commonly referred to as the virus, but really it's the virion. It is the transport form of the virus. It binds to the surface. Another theory is that it binds and makes an endosome and is sucked into the host cell. The host cell is the big gray thing here. And the virion contains 4 structural proteins and RNA and a double lipid membrane. The RNA is encapsulated by one of those structural proteins shown in gray, the nucleocapsid, and then is translated, among other things, into polypeptides. And these polypeptides then have to be cleaved. And only then do they become functional enzymes and can kind of like infect the host cell, which is why the cleavage mechanism, RNA, so basically this thing can cut itself, and inhibiting that would stop the infection. So the so-called proteases, which cleave the polypeptide, are a major drug target. We are also working on with Manfred Weiss and Rolf Hilgenfeld, but other groups like the COVID Moonshot Project, for example, have targeted them as well. From the polypeptide comes 16 non-structural proteins. And yes, that's their official name. They have a structure, but they're called non-structural proteins or NSPs because, well, they're not part of the virion. And in the endoplasmatic reticulum, which then bubbles up in the host cell, more RNA and more proteins are produced to form new virions in a packing process, which is not quite as well understood. We know something about the curvature of the membrane. And new virions are excreted from the host cell in masses. And this is the cycle of infection, also called the life cycle, although it's debatable whether a virus really lives. And then we have 8 proteins, they're called so-called accessory proteins. Their function is mostly unknown. Their structures are also mostly unknown. Out of the 28 you see here, we only know 17 from experiments, in part. Typical drug targets for COVID-19 drugs is the main protease. That's a part of that polyprotein that cuts the polypeptide into functional bits. And here you can see an inhibitor. So I think it's extremely likely that we will see a drug that targets that. Another important structure is, of course, the spike on the surface of the virus. You may have heard it mutates. How it interacts with antibodies and the host cell is, of course, a very important matter. I also have a model here, which we printed. So this is an antibody. I hope you can see that. And this is the spike. And the antibody binds to the spike. And of course, you can get the antibody from being vaccinated with something carrying the spike with no coronavirus on the bottom. For example, with an RNA vaccine that produced the spike in your own cells, or a vector vaccine with a harmless virus carrying the spike. And then you build those antibodies, takes a few days, you've got an immune reaction, possibly don't feel so well. And then you have those, and when the real coronavirus comes, you're equipped. So stand yesterday, we have 1,485 structures from SARS-CoV and SARS-CoV-2. From SARS-CoV, there were only about 180 in the beginning, right? So January last year, 180 structures, and that's the time that I kind of like foolishly thought, oh, perhaps I can improve a few of those structures. But meanwhile, it's been almost tenfold as many. And they come mostly from X-ray crystallography. Some come from NMR, one solid state NMR. Also, in addition to the X-ray crystallography, there are 2 from neutrons, both main protease, and 390 from the newcomer in structural biology, cryo-electron microscopy, which is the only technique that can resolve the RNA polymerase. RNA polymerase makes new RNA for new viruses, and is therefore a very important structure, because if you could stop RNA polymerase, the more RNA for new viruses couldn't be produced, infection cycle would be broken, and we would have a drug against corona. So we saw errors are common, structures are necessary to develop drugs and vaccines, And now we add to this an ongoing pandemic. And scientists being the one to rescue the world. Basically, this is a situation that is at the same time really great for us as scientists and really scary. Because we're under a lot of pressure, potentially being in lockdown at home with the children, doing homeschooling without contact to our colleagues. It is not to be assumed that errors would get less likely in structure solution in such a situation. So we basically decided to do what we must because we can. We were, in the beginning, there was me, and I checked a few structures in January and then started giggling and making jokes for about 6 weeks about how I could vet all those 180 structures. And then I became serious by accident on the day this was declared a pandemic. And we started the Coronavirus Structural Task Force formally on the 18th of March with my postdoc, Union Gao, and a few students who had volunteered to do their bachelor thesis in my lab, but were stalled by the pandemic. In the first week already, we were joined by Gianluca Santoni from ESF and Tristan Kroll from Cambridge. So Gianluca was collaborating with me on the ice ring thingy. That's gonna go in Ice by B, so I'm happy about this. And Tristan had just tweeted about structures having errors. So we kind of phoned him up. So I went through the entire Cambridge phone list of like, I think on that day I phoned with like half of Randy Reed's group. And I got hold of him and I just went like, hi, Tristan, I know we haven't talked for 2 years, but would you like to join us? We're doing a thing where we validate all the coronavirus structures. And do you have the chat messenger we are using? And he said, yes, and joined us. And then people came over the course of time. Sometimes we were notified that they are validating structures and we asked them whether they want to collaborate or join. Sometimes they approached us and said, hey, I am currently having time because I'm in lockdown. I would like to do something with you. I'm a structural biologist. And sometimes we recruited them, mostly student helpers, by asking them whether they want to help us for a small pay. And we also had a volunteer assistant and a volunteer media designer and a volunteer web designer in the beginning. So it was all very like resource scarce, and there was no money actually assigned to the project officially until July. So we knew kind of that we would get some permission to use money for the project, but up until July, from like March to July, this was funded exclusively from overheads that I happened to have because some lucky purchase in the same year. So this was totally unconventional and possibly only worked because everyone was willing and we were all in lockdown. And we were methods developers. Most of us were methods developers, as in specialists in solving structures and also writing the software you use. And we looked at all the published structures from the 2 viruses and human interaction partners, and we reprocessed and remodeled them, and then we do dissemination. I'm going to talk about this in a little bit more detail. So every Wednesday, the new structures come in the PDB. We download them by comparing them to the NCBI proteome of the virus, do a sequence comparison, do an RMSD calculation to existing structures, and then suck some data into an SQL metadatabase. We look if raw data are available. Unfortunately, they often aren't. And then we have an automatic pipeline that runs a lot of more or less known validation. Some of it, like, for example, Haruspecs or our more probity, are kind of bespoke, not published, or parts of Auspecs we're currently using have not been published and are not available. So we made good use of our contacts in the methods world to do something that kind of like was mostly standing on the shoulders of giants, but we also needed to adapt some things and like fine tune. And then some structures which are representative, for example, of a certain protein or important, very important for drug development, go into a manual refinement for which we use XDS, isolderefmix, CCPM, and Auspecs, depending on who it does, right? So all the manual refinement is done by postdocs. This is something that cannot be given to the students because they lack the experience. It needs to be someone who's actually certain to tell the authors that is not a magnesium there. And then we contact the authors when we have done a manual refine. And if we found something, we contact them and say, here's an improved structure, no strings attached. Please update your PDB. You don't need to name us. bye-bye. Because we really wanted to fight this pandemic, and we really didn't want to put any barrier between an update of these PDB entries, because we knew drug developers were dependent on them. All structures, whether manually looked at or only automatically, go into dissemination at GitHub and can be downloaded from our GitHub or our homepage. We regularly tweet. 3D BioNotes is an entrance to our structures. We also do public outreach. We did all the Proteopedia entries for corona structures so that the public may be informed about what is important literature, how they are folded, general overview. The MOL SSI Institute, which is a virtual institute for drug discovery and bioinformatics, is also directly linking in our database. On the homepage, you can get reviews for scientists on the different protein structures, as well as blog posts for the general public, mostly about structural biology. Today, we had one come out about mask materials. If you want to write a guest blog post entry about corona topics, please contact me. We're always looking for interesting guest blog posts. And we found some things. So one of them is modeling problems. So this Ramachandran plot isn't looking good. It's also very old, and it is an NMR structure, which is pretty old, so it's a little bit unfair, but it's such a striking example of like, okay, I bet this could be improved somehow. Here's another one. So this happens very often in the COVID moonshot things. The ligand structure is, this is the ligand, and this is the main chain, and the main chain suddenly has one residue which is not at full occupancy, and this comes from the pipeline they're using. But there is like a few dozens of COVID moonshot structures which have like full occupancy, full occupancy, full occupancy, half occupancy, full occupancy in their residues. And I think that's not kind of ideal. Here is also a fairly common one. Zincs are a huge problem. Zinc ions seem to be really a huge problem in all of corona structures. It's the 5th most prevalent element. It is also very important biology-wise for the coronavirus. But here there's a disulfide bridge instead of the zinc in the zinc finger. And that's just a modeling problem. If you put a zinc here, it fits better. But you can possibly not tell from this density that there should be a zinc here. I mean, it's not kind of high resolution. You need to know this is a zinc finger domain. And actually this one, we wrote to the authors and it was fixed. So it's not there anymore if you look now. Here's another one. So histidine being in the wrong conformation to coordinate zinc. Zinc only has like 4 coordination partners typically. So the histidine should be putting one of the nitrogens in the direction of the zinc. Then trans and cis problems are also fairly common. Here is one corrected, which is pretty obvious from the density once you're looking. And this one is fairly common and we don't know why. So this is a glycosidic bond chirality, which is wrong. So the sugar is binding to the protein, which is normal in mammalian cells and is important for coronavirus infectiousness. But somehow the chirality is wrong, and as a consequence, the density is not really nice. And if you like flip the chirality to the correct known chirality, it fits much better. So lots of potential for automatic corrections, improvements to modeling, and these are actually all very nice examples of things that can be fixed with today's software. Also problematic was the structure 7BV2. 7BV2 is the RNA polymerase. Remember the RNA copy machine, which makes new RNAs for the virus. And remdesivir blocking it. That was at least the claim. And the problem with this is that this should show that remdesivir is a drug that would work against corona. So this is the mechanism. Remdesivir is taken in by RNA-dependent RNA polymerase. As the RNA polymerase thinks it's a nucleotide analog, and it can build it into RNA. And one problem with all RNA polymerase structures at one point was that the first one was low resolution in the C-terminus, and therefore it was very difficult to assign the sequence because there was a missing loop before it. So, you know, amino acid sequence along the protein. And it had a rather large so-called register shift. So the sequence was not aligned correctly to the main chain. And this is Isolde, Tristan software, correcting for it. And now it's nicely fitting and needs a little bit of wiggling. So it does molecular dynamics in kind of real time while you're dragging around on the molecule. And I only started to learn Isolde during the last year, but it is exciting to use. It's a bit like video gaming. And we found that 17 structures had this out of register shift by 9 residues in the C-terminus. And then we wrote to all the authors, and I can now report that no new RNA polymerase is having this problem. It's been widely tweeted, and because everyone was alert about it, it didn't happen again. So we found it, it got corrected, and no other structures were published that have a problem. And that's good because that little helix at the end of the C-terminus is actually interacting with the RNA. Another problem with 7BV2 RNA polymerase, here's the cryo-electron microscopic map, which represents the experimental data. Here is green is the template strand, orange is the new strand, and remdesivir, which is actually bound but not shown as bound, is down here, was in the structure. And also in the structure was diphosphate and 3 magnesium ions. And they had been predicted to be there in part by biochemistry. At least one of the magnesiums should have been there. And if we now have a closer look into this, so I'm rotating it first so we can see the binding pocket. So this is the new strand of RNA. This is remdesivir, which is bound here. I just didn't paint the bond. And then you look at the density, you can actually see that at this level and others, the magnesiums and the diphosphate have little or no density, which means they're not there. There is no experimental evidence for them being there. So we kicked them out, wrote to the authors, and see there, they corrected their structure. And I think even before the paper came out. So that was good for drug developers because drug developers would have taken this structure with remdesivir as a template to make new inhibitors for RNA polymerase. And the diphosphate and the magnesium would have led them to totally different drug compounds. We published recently, finally, after like months of writing, editing, more editing and more editing, and with 24 co-authors, there's a lot of editing, the main reference for our work. Although I would like to point out, this is an open science project. And if you really want to know about it, I would much rather recommend the homepage than reading the paper. But if you need to cite us because you're doing something based on our work, please cite this. It's going to help us. And we also developed animations, most of all this entry animation with Janet Iwaza at Utah, who also helped us with the life cycle. So here you can see the coronavirus. And this is based as much as we know on the structures. So it also clearly shows that we don't know some things about entry. Here's the coronavirus, and at the bottom is the host cell. And it's got AC2 receptors and TMPRSS2 receptors, and these are common in lung cells. So this is why the coronavirus tends to bind to lung cells. So what we know is the spike binds possibly with 2 spikes, we think, possibly 3, but one seems a little energy onto the AC2 receptors. And then it gets cleaved by other surface proteins and refolds. And this refolding bit is a little bit unclear. It ends up somehow sticking in the host cell, mammalian host cell membrane. But how exactly that works, we have no structures because this is an intermediate state. And as you know, in structural biology and crystallography, we cannot really see intermediate state unless we find a way to fix them. And then this is unstable, and we know this, and has to refold like a spring mechanism, thereby dragging the virus and the host cell together, which allows, whether it's in an endosome or on the surface, the RNA and the nucleocapsid to enter the host cell and start the cycle of infection. So it was really cool to do this. But I also have to say, once you have to animate something, you understand what are all the things you haven't understood about the biology. I can only recommend it. It's very, very healthy and cleansing experience. This is our homepage. These are our blog posts. These are our partners and downstream users. We were particularly excited about the JEDI Grand Challenge in Europe, so European Union, which was a challenge for finding a drug. Open Pandemics, so IBM Open Pandemics is using our data mostly now, and Folding at Home also is using our data. We collaborated with a lot of individual labs as well, and we also counsel them on occasion if we can. And then I quickly wanted to show you, this is the CDC picture that you see everywhere of the virus, and the spike heads are sticking in the middle, oops, in the middle. So there's no stalk, but in reality, of course, the spike, while we have only mostly structures of the stalk or the head, well, there is a stalk, which is shown here. And the surface is actually not round. The virus is not round, no matter what people tell you. It is wobbly because it's like a soap bubble. It's got a double lipid membrane. It's not very stable. It can also vary in size quite a bit. Like estimates are about 1/3 bigger or smaller. It's also huge. The RNA is one of the longest among viruses. So you can see here, I hope you can see this, although the presentation is on. This is a rhinovirus, so it's common cold. And this is a coronavirus in the same size. So it's really huge. So we made those models, and these models were actually made by Thomas Splitt-Stößer, Del Tronrud, and my students. Painting was done by Christopher Nolte, who's shown here, and did a very successful bachelor about the ice rinks in my lab. And Louise, who's programming a plugin for Qt, but occasionally they just resorted to handicrafts. And this can be downloaded from Thingiverse. It's free for all. You can download it and print it at your own institute. And schools also use it. And we are currently preparing some school materials to go with the model and developing a new model which has springs as the stalks of the spike because it can bend. And yeah, in the last 5 minutes, I quickly want to talk about life in coronavirus structural task force and coronavirus times. So it's definitely been both horrible and awesome. This is us today, plus Jane Richardson and Christopher Williams. So we are 25 people today. We've been fluctuating about 25 for a while. About half of the people are from my lab. Most of them are students. The rest are postdocs and professors. And Alex, who's a PhD student from all over the world. So we span 9 time zones. And that alone makes discussion a little bit difficult, but we meet every day at 10 o'clock and on Wednesdays at 1600 to talk with whomever is working on that day on Corona. And this is very nice because it means that every day at the start of my day or an hour into my day, I see all the faces, and that has been a tremendous help for structuring the work. It also gives the students a reason, I guess, to get up. But some of them are really early risers and much earlier than me. In any case, at 10 o'clock, everyone focuses on the work, and then at least until lunchtime, there's some productivity going on and some communication. We, this is the wrong order. We also have a group chat. And this group chat is not like your typical scientific mail. It's more like very wild exchange of young people and older people talking about papers and memes. And some of it is serious and some of it isn't so much. But it's been really helpful to have this kind of like social support group of friends who were all in the same situation and researching the same thing during the pandemic. And I really think that it is of course ideal to be together in the same room at an institute and to do research together and just have that kind of mobility to be at a place where you don't do research. But there are people in this world who are good researchers and who cannot come to institutes because they're handicapped, because they're caring for their parents, because they have little children, because of reasons. And for these people, working virtually can really be an avenue. So I think that we gathered a lot of experience with this, and I'm very happy to discuss it with other people. Now back to that other slide. Press. Press happened from April, I think, and I was shocked because I'm a methods developer in crystallography. The only press experience I had was an interview about textile weaving at the museum like years ago. And then German national TV wanted to talk to me, and the newspaper wanted to write to me, and I had a live interview in television. And it was a very steep learning curve. And I desperately always try to give the journalists my students, but they always want to talk to me as well. And they also made comments like, this is what it looks like when geeks save the world. And there's absolutely no article about me which doesn't comment on my hair and my eyes, which I find, frankly speaking, weird, because no one talks about the eyes and the hair of male scientists. But after all, it's going to be some little girls possibly going to look into the newspaper of her parents and go like, Mom, I want to be a scientist. So worthwhile. My media competency has risen. We had the good and the bad, and most journalists were pretty nice and tried really to understand what we were doing. And I can recommend it as an experience. You need a good press office. That's the other thing I also learned. It was exciting. But also if a journalist comes, the rest of the week is usually like, you spend like a day or two on this. It's really taking a lot of time. So I reduced the number of interviews and media stuff I did in favor of like going back to writing more papers and doing more science. We also did some other things. So it was often requested to me by certain members of this group that they would only work for stickers from a certain point forward. So we printed stickers when we got the grant. We're tweeting, we're twitching. You can watch us refine it. Actually, Sam Horrell from Diamond Light Source. One very nice person sent us Krisenhelden, which is crisis hero masks. We have a cactus, Corinna the Corona cactus, which the students brought into the lab and is currently being watered by Institute Director Arwen Pearson, our scientific fairy godmother. And we also do YouTube. So if you want to see that animation from previously, again, go to YouTube. And our channel is called Thorn Lab. And we did these things because it was a horrible time. Don't get me wrong, we take this pandemic totally serious. We had several like Corona cases close to us. It was like bombs were falling left and right of us. But the only way to survive this was to be sometimes joking and sometimes just trying to cheer each other up. But I don't want to be misunderstood as not taking all of this work very serious. We also have some virtual spaces that we like to hang out at, like Work Adventure. And we also play games after hours, sometimes together, because we were so stuck. And in particular, the students were really alone in their dorm rooms and not allowed to go out. In order to understand the virus and its life cycle, you need to understand its molecular biology, its structures. That will help us to design drugs, and I hope a drug is going to come soon. And it helped us to design vaccines. We evaluated these structures with a bespoke pipeline and expert knowledge. We also provide context for people who want to embark in Corona research or need context for a certain structure as bioinformaticians. Structural biology, however, remains difficult. What can we learn from our findings? Should we change our attitude towards errors and people who make them? Should we change how we see models? I think we should. Should the coronavirus structural task force serve as a model for other projects? I have been asked this first by a Nature editor before we actually submitted our paper, and I think it could. I must say that this was the most enjoyable research collaboration I ever had, and it's still ongoing, and I love it. But better funding would be very desirable the next time. So it will not happen again as spontaneous willingness. We would need to do this differently and possibly with some more administrative support. You have to think, in 2018, I became a junior group leader. In March 2020, I hired my first postdoc. in July 2020, I was heading a research collaboration of 25 people and spoke to the media. It was a steep learning curve. I had to train my leadership and media skills while I was doing science, which millions of grant money depended on down the line in drug development. It would have been nice to do this with a little bit more support, although I must say that now that all had a little bit time, I'm getting more support, and I got a paid assistant recently, and I now have a second in command, so I can finally go on holiday without worrying that I'm not there, because there's someone to replace me during that time. How old do you really need to be to do such a project? Some of the reviews we write are written by 24-year-olds. I am like 38. I don't understand why you need to be a professor to initiate projects. In particular in America, you need to be a PI in order to get grants. I don't understand this. Why do you need to be so old? People gradually become ever older as they become professors and postdoc periods get longer. And it's something we all suffer from. It also makes it hard to have a family. I don't understand. I think that the system could change, and Corona may hopefully catalyze some of this. Can open science compete? We needed to publish a paper, we'll possibly publish another one. What will change in science after the pandemic? And how will we as scientists be viewed by the public after the pandemic? With this, I'm at the end. I would like to thank, first of all, the 25 members of the task force who really constituted my peer group during the last 15 months, and without whom nothing of this would have happened. Our collaboration partners who believed in us and who we helped with our expertise to solve problems surrounding the pandemic. The people who collaborated with us, like PDB Redo, Thomas Spletschdös at the Animation Lab, who helped us to bring this across. And our main funding comes from the Bundesministerium für Bildung und Forschung, so the Federal Ministry of Research and Education in Germany, and the DFG. We're currently hosted at the University of Hamburg, although the project started at the University of Würzburg. We're currently looking for a web designer, ideally a German student, but we could possibly accommodate others as well. Please write me an email, and guest blog entries, as I already said. And I'd like to thank you for listening. I would ask you to switch on your cameras if you want to join the discussion, or just show me your faces. And I'm happy to take your questions.
Wow, thank you very much for this very impressive and totally amazing talk. I just gave everyone the permission to unmute themselves and start a video, and I'm pretty sure there must be some questions. Maybe I can start. I was really, really impressed by your talk, also like what you have achieved within such a short time, and just like so much spontaneity and all at the beginning, kind of involuntary work. It's like really, really impressive. Maybe very random. I was impressed by the structure where you used molecular dynamics to resolve the structural error in the thing. How does that work?
Well, actually, in that case, it wasn't the molecular dynamics itself which solved the problem. It's the fact that the SARS-CoV-2 structure had a much higher resolution than the first structure where the error was modeled. And in that newer, higher resolution map, it was obvious that the side chains didn't fit, so the sequence didn't fit. So in that case, it wasn't molecular dynamics which solved it. It was just the Isolde software which uses molecular dynamics we used to correct that. But in other cases, the molecular dynamics in Isolde can kind of like help you forego other geometry problems, because the force field is constantly dragging you in the right direction and trying to fit everything and constraining or restraining everything it makes it easier. It also makes you easier to get a feeling for how much of an energy barrier something would have to overcome in order to go in a different conformation. As you're dragging on it, and you kind of like know how much you have to drag it in order to snap into that different conformation, or it immediately snaps back, and you know it is not stable under the assumption of bond lengths and angles. And van der Waals repulsion, of course, so clashes. But Tristan published actually, and I didn't show that, possibly should have put it in, his own paper with Jane on, it's called Peer Review by Early Coordinate Release. And there he kind of like unpacked some of the things he did, in particular with Isolde. And they actually published it thinking that our paper would come first. But in the end, we were 2 months later than they were. And there are authors on both.
Okay, thank you. I see that Concelia has a question.
Hi, thank you for this very inspirational talk. Could you give some details about your interaction with the PDB, and how do you, do you follow a specific protocol for that, or did you invent it? And what's for the future? I think this is a start. We need better structure, and we also need a choral effort. So we are scientists, we can do something. If we find an error, possibly this is only because we are human. Humans make error. And this is
I also think it's really important to say that we are trying to get the best out of the data and take away from blaming people. I think that we should blame structures. We should blame interpretations. We can blame this, but blaming people for making errors in a field as complicated as ours is just gonna cost us junior researchers and nerves. And we all just need to be more teachers of each other and be benevolent. So our interaction with the PDB was that in the first week already, I asked Samir at PDBE for a conference, and we talked about their knowledge base, which they were building up. And we interacted with them every year and then, mostly about how to search their data, tying in with them. However, we cannot funnel the correct structures directly back. There's no way to automatically submit a structure based on another structure that has been published, and the only people who can version the original entry are the original authors. And this system makes it virtually impossible to do basically a deposition of routine improved structures, which is why PDB redo is also a separate database. And the problem is also that the PDB are not very well funded. In terms of like, you know, they're free service, they're only like taxpayer funded. And so they cannot bring this kind of like vetting. But an ideal dream for me would be something perhaps working like GitHub, where you, for example, I find there's no magnesium ions in the structure. I upload it to my PDB GitHub thingy and make a pull request to the original author saying, dear original author, I improved your structure. I changed this and this and this. Please have a look at it and accept if you think it is valid. One problem you could have with this is while software developers at GitHub always want to improve their software, after initial publication, scientists, structural biologists don't like to admit that their structure could have been better. There is no gain for them because the paper has been out and is being cited. The gain would really be for the downstream users and the people who come after them. So I think this is an almost philosophical discussion that the community needs to have. What can we do? I'm sorry for not being able to present an immediate solution, but I think we need to have that conversation, even with all the constraints that people are quoting.
Yeah, I totally agree. And this is about time, I think. Thank you.
Are you planning to have this conversation, for example, at the upcoming IUCR? Or like, how would you like to start it?
I'm going to give a keynote, which may be similar to this talk at the IUCR However, it may be I am still a junior researcher. I am not sitting in any validation task force. I'm not on the board of PDB. I'm not yet a community leader in this research community. I hope to become one day. And if I become, I'll have this conversation. I'd be very grateful if we could have it earlier. And there are a few people here in the audience who would be able to start it with more force. And I think I can speak for every postdoc and PhD student in my team. We'd all like to be part of this discussion. We have seen a lot now. We have this subsample of 1,500 structures now. We know which errors are common. We have looked at them closer than many other structures have been looked at. I mean, there have been like the top 8,000 data set, for example, from the Richardsons. And I'm sure Robbie Houston has a share of structures that he's looked at very closely, statistically. But the problem is even exacerbated by AlphaFold, because if you think about it, AlphaFold is trained on a PDB, meaning it is trained on structures that represent only like ground states that are energetically stable, folded, and could be refined with current methods, including all the errors people may have made because, for example, they applied Ramachandran restraints. So we have a machine learning algorithm, but it can never be better than training data. It's just I didn't show this, but my lab is developing machine learning methods for data analysis and model analysis. And you can never be better than your training data. So if we use the PDB as training data, there's another big reason to have this conversation. Sorry, this is all I can say about it right now.
Sure, and I'm glad you made also this awakening call for like reminding that, yeah, we should talk about it. Maybe Camille, as a very last quick question, please.
Yes, thank you very much. Very nice talk. Could you we go back to this intensity versus resolution plots, because they are quite interesting. Could you briefly comment on what's the role of the radiation energy? Did you look at it in these plots, and also in view that the higher the radiation energy, the lower the scattering factors, but then of course the radiation damage is probably less.
Do you mean energy in terms of the intensity of the beam, or in terms of the length
of the energy of the radiation?
So the wavelengths.
Yes, you mean.
Yeah, we didn't do any analysis of this yet.
Okay.
So what I know is we can only see effects in these plots, which are really exacerbated. And what I also know is that depending on how the data were collected, we see very different things in sigma. So in the standard deviation for each intensity, and even worse after they have been converted from intensities to amplitudes, which is something that macromolecular crystallographers do, because the so-called French and Wilson formalism for converting intensities to amplitudes assumes a certain statistical distribution, which is rarely adhered to. And the consequence is that even if your standard deviations were just a little bit strange, because, for example, your data came from an X-felt source, after the conversation to amplitudes, it's a catastrophe in terms of standard deviations, and sometimes also in terms of the amplitudes. And we are seeing some really strange effects for these novel sources. I can like reasonably demonstrate that neutron integration could be much better just by these plots. And if the corona pandemic wouldn't have hit 15 months ago, we would have started to go into depth with this after having been funded. But we put all our energy towards, or most of our energy towards corona right now, and the project has been delayed. Perhaps in Versailles, if you're there, yeah, and you can also send me an email and propose what we could analyze. Making the analysis is relatively quick.
Sure, that will be great. Thank you so much again.
Okay, I think with that, we are almost at the end. Thank you very much, Andrea, again. That was really impressive and a great talk.